Whenever you plot a graph of position of an object or a particle versus time, you can call it as a PT graph. Please remember, any curve represents acceleration. If it is pointing upwards, it represents positive acceleration. If it is pointing downwards, it represents negative acceleration. So V0 is initial velocity, V is final velocity, T is time, and X is displacement. Hello students, welcome to this second session on the chapter Motion in a Straight Line in first PUC Physics. I am Madhu R from the Department of Physics at Vidhyaashram PU College, Mysuru, your temple of excellence. Let us begin this session by recalling what we did in the first session on motion in a straight line. We studied about motion and rest. When do we say that a body is in motion, or when do we say that a body is at rest? We understood what was path length and what was displacement. We also understood that for speed we consider path length, whereas for velocity we consider displacement. Displacement, as you all know by this time, is the shortest distance between 2 points. We understood what was average and instantaneous velocity. We studied the concept of acceleration, where acceleration is the rate of change of velocity with respect to time. We also understood what was uniform acceleration and what was instantaneous acceleration. So let us move on and try to understand further concepts like PT graph, VT graph, and kinetic equations of motions today. Now, what is PT graph? P stands for position and T stands for time. So whenever you plot a graph of position of an object or a particle versus time, you can call it as a PT graph. The PT graph plots an object's position on the y-axis against time on the x-axis. As you can observe here, position is plotted on the y-axis, whereas time is plotted on the x-axis. As we all know, the rate of change of position with respect to time is velocity. So if you take the slope of this PT graph, you will obtain the velocity. For an object moving in a straight line, the slope of this graph directly represents that object's velocity. Let us check which type of graph represents what motion one by one. Suppose a particle is at rest. A horizontal line represents an object at rest. Okay, as you can see, a horizontal line here will represent a particle or object at rest. As you can see, with respect to time, there is no change in position, which means that it is at rest. Okay. Then, uniform motion along a straight line. If the motion is uniform, okay, if the motion is uniform, constant velocity along a straight line, it is represented by an inclined line. It is represented by an inclined line. See, whenever this is represented by an inclined line which is positioned upwards or pointing upwards, you can say that it is positive velocity. Similarly, if an inclined line is pointing downwards, then we say that it is representing negative velocity. Please remember, straight line represents what? Straight line represents uniform motion along a straight line. Okay? If the inclined line is positioned upwards, it is positive velocity. And if the inclined line is pointing downwards, it represents negative velocity. Then what about acceleration? Any curved line represents acceleration. Please remember, any curved line on the PT graph will represent acceleration. What type of acceleration? If the curve is pointing upwards, it represents a positive acceleration. Similarly, if the curve is pointing downwards, it represents negative acceleration. Please remember, any curve represents acceleration. If it is pointing upwards, it represents positive acceleration. If it is pointing downwards, it represents a negative acceleration. If it is a straight line, it means that acceleration is zero, constant velocity along a straight line. There is no change either in velocity or direction, which means that acceleration is zero. Okay, is that understandable? So we have studied The PT graph for an object at rest, for an object in uniform motion along a straight line, and we have checked how acceleration is represented with the help of position time graph. Now let us move on to one more type of graph, which is the VT graph, where V stands for velocity and T stands for time. As the name suggests, whenever you plot velocity versus time, it is called as VT graph. You are plotting velocity versus time. What happens here? The slope of this velocity versus time graph will give you what? See, I have got velocity on the y-axis, time on the x-axis. What is rate of change of velocity with respect to time? Rate of change of velocity with respect to time is nothing but acceleration. So if you plot the graph and take its slope, you will obtain acceleration. Similarly, whatever is the area under the curve, the area under the curve will let me know what is the displacement. Area under the curve will give me the displacement. So what are the uses of this VT graph? This is a popular question from your examination. What are the uses of this VT graph? First and foremost, it lets me know the nature of the motion of a particle. What is the type of motion? Is the acceleration positive? Is it in positive direction? Does it have some initial velocity? All these things can be known. Then, instantaneous velocity and instantaneous acceleration can be found. I can find the velocity and acceleration using this curve. I can also find the displacement. I told you, area under the curve will give me the displacement. Ultimately, I can derive the kinematic equations of motion. I can derive the kinematic equations of motion. If you can remember your high school physics, you had equations like V is equal to V naught plus AT, so on and so forth, where V is the final velocity, V naught is the initial velocity. We will be deriving these equations in the next slides. Okay. So what are the uses? I can find the nature of motion, I can find velocity, I can find acceleration, I can find displacement, and I can also derive the kinematic equations of motion. Okay. Let us check what are the types of acceleration, how it is represented in this velocity versus time graph, one by one. The first one, when an object is traveling with uniform velocity, there is no change in velocity. It is represented by a horizontal line. Okay, there is no change in velocity, which means that velocity is uniform, represented by a horizontal straight line. Next point, negative acceleration. What is negative acceleration? Acceleration under velocity time graph is represented by a slant line or an inclined line. If that inclined line is pointed downwards, the acceleration is negative in nature. Please remember, if the inclined line is pointing downwards, the acceleration is negative. On the contrary, if the inclined line is pointing upwards, okay, with some initial velocity, then this is called as positive acceleration. Okay. If the inclined line is pointing upwards, it is positive acceleration. If the inclined line is pointing downwards, then it is negative acceleration. If the line is horizontal and straight, then it is uniform velocity and there is no acceleration. Okay. Let us check certain conditions here. Motion in positive direction. When do I say that the direction is positive? See, I have got four quadrants. This is x-axis, y-axis, positive. This is minus y-axis, this is minus x-axis. Whenever there is the motion in the first quadrant, I call it as positive direction. If it is in the fourth quadrant, I call it as negative direction. Okay. So if the acceleration curve is in the first quadrant, it is positive direction. If it is in the fourth quadrant, it will be negative direction, which means that if it is in negative y-axis, then I call it as negative direction. Okay. Let us check. Motion is in positive direction. Okay. So it is above the x-axis. Motion is in positive direction. With positive acceleration, the acceleration curve is pointing upwards. The inclined line is positive, pointing upwards. So this is positive acceleration having some initial velocity. Please observe, this inclined line is not starting at 0. It is starting at some point where the initial velocity can be considered to be V0. Okay. So what does the condition say? The motion is in positive direction, which means that it is above x-axis. Positive acceleration, the inclined line is pointing upwards with some initial velocity, which means that the line does not start at 0, 0, it is starting somewhere above the 0 point on the y-axis. Okay, so this is first condition. Let me check the second one. Motion is in positive direction, so this is above the x-axis. Motion is in positive direction. Negative acceleration, the acceleration is negative, the inclined line is pointing downwards and it has some initial velocity. It has some initial velocity. The inclined line starts at some point above the 0, 0 point on the y-axis. Okay. So motion is in positive direction, acceleration is negative, pointing downwards. It has got some initial velocity V0. Okay. Let us check a couple of more conditions. Motion is in a negative direction with negative acceleration having some initial velocity. Okay. Until now we studied two conditions where the motion was in positive direction. It was above the x-axis. Here it is below the x-axis. This is x, this is y, this is minus y. Okay. So whenever the motion is below the positive x-axis, I call it as a negative direction. Now let us observe the curve, the nature of the curve. Negative acceleration, the curve is pointing downwards. The curve is pointing downwards. So the acceleration is negative. And it says that it has got some initial velocity. There is some initial velocity. It is not starting at 0, 0. Okay. Negative direction, negative acceleration, some amount of initial velocity. Finally, we'll study one more case so that you get a clarity on what are the types of velocity graph that you can draw versus time. Check here. It has started in the positive direction. It is above x-axis, but it is ending in the downward direction. Okay. It's a classic case. The acceleration is negative because it is pointing downwards. It has got some initial velocity. Let us check what it is. Motion of an object with negative acceleration. Acceleration is negative, pointing downwards. Negative acceleration changes its direction at time t1. See, at time t1, it changes its direction from positive to negative. It was positive up till time t1, but after time t1, it changed its direction to negative. So it says motion of an object with negative acceleration that changes its direction at time t1 having some initial velocity. So these are certain different types of graphs that you can plot whenever the variation of velocity with respect to time can be considered. Okay. Let us move on now and check how kinematic equations of motions can be derived. What are kinematic equations? Kinematic equations for uniformly accelerated motion. Please remember, this is for uniformly accelerated motion. For uniformly accelerated motion, there are 5 different types of quantities that are considered. Displacement is there, time taken is there, initial velocity is there, final velocity is there, and acceleration is there. Okay. So you are plotting or deriving equations among these 5 physical quantities. What are these 5 physical quantities? As I said, displacement, time, displacement represented by x, time represented by t, initial velocity by v0, final velocity by v, and acceleration by a. These kinematic equations will let me know the relations between these physical quantities. for uniformly accelerated motion. So when I say uniformly accelerated motion, you will have one inclined straight line. Okay. What are the equations? As you already know, V is equal to V naught plus AT. For displacement x, it is V naught t plus half AT square. Final velocity V square is equal to V naught square plus 2AX. These are the three popular equations of motions. Let us try to derive them one by one. What is the first one? The first relation is V is equal to V naught plus AT using the velocity time graph. See, we have already stated that the kinematic equations are for uniformly accelerated motion. So, for a uniformly accelerated motion, the graph is represented by an inclined line. Okay, where there is some initial velocity V naught. Okay, and then there is some final velocity V. Okay, there is some final velocity V. You can see that it is represented by this. So this is the graph AB. Let us check how it is done. Consider a body moving with uniform acceleration. The acceleration is uniform. This is the first thing that we have taken into consideration. Let V naught be the initial velocity, V be the final velocity, and T be the time taken. When I plot a graph of V versus T, that gives me the acceleration. What will give me the acceleration? The slope of this graph, see, this is the slope. The slope of this graph will give me acceleration. What is that slope? It is BD by AD. I have to check BD by AD. So, slope acceleration is given by BD by AD. Let me check what is BD and what is AD. See, observe here. I can write BD as, BD can be written as BC minus DC. Can you observe from the sketch? I can write BD as BC minus DC. Why? Because BC represents final velocity, BC represents final velocity, and DC represents initial velocity. Okay? Then what is AD? You can see AD is the time taken by the body to travel from A to B. So if I replace all these terminologies, I get A is equal to V minus V naught by T. When I cross multiply, I get V minus V naught equals AT, or V is equal to V naught plus AT. This is the first kinematic equation of motion. What is it? Final velocity is equal to initial velocity plus product of acceleration and time taken. First equation. Okay. Let us move on and check what is the second equation. The second equation is for displacement. It is given by x is equal to V naught t plus half AT square. What do? I once again plot a graph of velocity versus time for uniform acceleration A. Okay. I plot the graph and then I try to derive this relation. What do? Consider a body moving with uniform acceleration A. Okay, a body is moving with uniform acceleration A from A to B. Okay, I have plotted the velocity versus time graph. Let V naught be the initial velocity, V be the final velocity, T be the time taken, and X be the displacement. So I have taken all the 5 quantities. Displacement. If you go back to uses of VT graph, we are told that displacement is given by the area under the curve. So whatever is the area under this curve, okay, that will give me the displacement. How to find the area under the curve? If you observe keenly, this OADC, okay, is a rectangle, and this ADB is a right angle triangle. So I know the formula for both of these. I can check the area and add it up. What is that? Area of the triangle ABD plus area of the rectangle OADC. How do you get the area of the triangle? Yes, it is half into base into height. So half base is AD and height is BD. Okay, so for area of the triangle it is half into base into height. So this is half, base is AD and height is BD. Similarly, for area of the rectangle, it is length of the adjacent sides, product of length of the adjacent sides. So I take OA and I take AD. So if I substitute, AD is nothing but time taken. Okay, OA is nothing but the initial velocity. Now what do I do for BD? See, check here, BD. I can write BD as I did in the previous equation. I can write this as BC minus DC. Or what is BC? BC is the final velocity minus V naught is the initial velocity. So what do? I replace AD by time, BD by difference of final and initial velocity, OA by initial velocity and AD by time. Okay. So if I can resolve this, what will this be? V into T. Okay. And then you have plus half A into T square. So finally I get the relation as X is equal to V naught T plus half A T square. Okay, what is it that I get? I get the relation like this. What did I do? In place of V minus V naught, I replace it by AT. How? In the first equation, V is equal to V naught plus AT. Okay, or V minus V naught equals AT. So the difference here, V minus V naught, it can be replaced by AT. So once I replace that by AT, I get this equation, X is equal to V naught T plus half AT square, which is the second equation of motion. Similarly, let me derive the third equation of motion. What is it? The third equation of motion says V square is equal to V naught square plus 2AX. I have similar considerations. What are those considerations? Consider any body moving with uniform acceleration A. Okay, so once again the graph will show an inclined line with the regular terminologies. V naught is initial velocity, V is final velocity, T is time and X is displacement. So when I plot the velocity versus time graph, I have an inclined line with some initial velocity V naught, final velocity V, and the time taken by the body to travel from A to B is T. Or the time taken by the body to change its velocity from V naught to V is T. Let us derive the equation. Once again, okay, what do? I take the displacement into consideration. How will I get the displacement? Displacement is given by the area under the curve. Uses of VT graph. We had discussed the uses of the VT graph. So what do? I take the area under the curve. Okay. Here I have considered one more type, how I can find the area under the curve. See, this looks like a trapezium. This looks like a trapezium. How do I find the area? It is once again base into sum of parallel sides. These are parallel sides and this is the base. Okay. So OC is the base, OA and BC are the parallel sides. The area is given by half into base into sum of parallel sides for this trapezium. Half into OC into OA plus BC. How do I get it? OC is given by T, whereas OA and BC, OA is V naught and BC is V. So when I take this sum, it becomes V plus V naught. But what is T? Okay, what is T? I know from the first equation. V is equal to V naught plus AT, V minus V naught equals AT, or T equals V minus V naught by A. Okay, this is what I have taken here. Substituting for T with V minus V naught by A. Please observe what you see here. This is V minus V naught, this is V plus V naught. Looks like A plus B into A minus B. What is A plus B into A minus B? Yes, it is a square minus b square. Okay, so this becomes v square minus v naught square by a into half, or v square minus v naught square is equal to 2 into a, and I cross multiply, this becomes 2ax. Okay, so what do I get? I get v square minus v naught square equals 2ax, or v square equals v naught square plus 2ax. I shift this term from LHS to RHS. So that gets me the third equation of motion, which is square of final velocity is equal to sum of square of initial velocity plus product of acceleration and displacement. Okay, is that understandable? Please note, we had considered uniform acceleration, and we had considered that the particle starts at 0 at time 0, at t equals 0. Now if I change that, what will happen? The set of above equations were assumed that at time 0 position of the particle is 0, which means that x naught was 0. At time 0 the position of the particle was at 0, it had not taken any position. Now what happens if it has some initial change of position? Okay, at time 0 the particle is already at some position 0, at some position x naught. At time 0 the position of the particle is not at 0 but at some non-zero value x naught. What will happen then? Then the equations will be, wherever there is displacement, instead of x you will have to write x minus x naught. First equation, there is no change because displacement is not involved here, there is no x. The second equation, it was x is equal to v naught t plus half at square. This changes to x minus x naught equals v naught t plus half at square. Similarly, third equation changes to v square equals v naught square plus 2 into acceleration into x minus x naught. So wherever there is displacement, because previously we had assumed that it starts at 0, there was no initial displacement or initial change of position. Here we have said that it is any non-zero value, x naught is some non-zero value, so that is why there is a change in position. This equation will be helpful to us while solving the numericals. We have come to the end of this session by now. What did we study till now? We studied position versus time graph or PT graph for different conditions. We studied velocity versus time graph, VT graph for different cases, positive direction, negative direction, positive acceleration, negative acceleration with some initial velocity. And the third topic was we derived the kinematic equations of motion. Okay, have a wonderful learning experience. Thank you.